Okay, so in this lesson we're going to be talking about matrices. So a matrix is a singular form of the word. Plural is matrices. So I've defined a matrix right here, and I just want to talk about why we're introducing matrices right now. So the last video talked about systems of equations, and a matrix is a systematic way to help us solve a system of equations, a system of linear equations. So before we can get into that, we need to talk about some of the basics regarding operations with matrices and just more about their properties. So back in the 1800s, mid-1800s, Arthur Cayley and James Joseph Sylvester invented what we call the matrix. And Werner Heisenberg used matrices in 1925 when he was developing his theory of quantum mechanics. So a matrix is something very useful, and there's actually a whole discipline of mathematics called linear algebra surrounding it, and some other stuff. But if you are interested in that when you go to college and it's in your major, you may take some courses called linear algebra, where you talk more about matrix properties and then some of their extensions. So we're going to talk about some of the basic properties today. But I do want to point out that the direction we're heading with this has to do with solving systems of equations. So if you watched that last video and that Gaussian elimination was not your friend, then a matrix, and the matrix system that we're going to be talking about in later videos, is an easier way to solve a system. We're still using Gaussian elimination in a way, but it's just an easier way to go about it. So we'll get to that later, but before we do that, let's talk specifically about what a matrix is. So it's a rectangular array of numbers enclosed in brackets or sometimes in parentheses. So I just want to show you an example. So 1, 2, 3, 4. So it's this group of numbers. This is a matrix. And it could also be in brackets, and it can have different dimensions. So maybe 6, 0, 1, 1/4, 2/3, and 8. It could be all sorts. So here's a parenthesis, here's a bracket. So this is my preferred way of writing them with brackets, but if you see them written in parentheses, it's not really different at all. It's just a different way of writing it. So there's no difference in the meaning of them. And let's do another one just so we can talk about things a little bit more. So 5, -1, 0, 4, 2, 3, 16, 112. Okay, so these are 3 different matrices. This is the first matrix. So together they're matrices. Here's a matrix. And when we talk about matrices, we name a matrix by its dimensions, and we actually name them via their dimensions, but it's a standardized way. So a long time ago, we decided to call them their number of rows by their number of columns. So this one has 2 rows and 2 columns. So it's a 2 by 2 matrix. This one has 3 rows, but still 2 columns. It's a 3 by 2 row by column, 3 by 2 matrix. 2 rows, 4 columns. This is a 2 by 4 matrix. Now, each of these numbers within the matrix is called an entry, or sometimes an element. So this is an entry, sometimes called an element. Again, it just depends on who's talking. I like to call them entries. Could be called elements, doesn't matter. So let's look at this matrix here. And a common question could be, what element or entry, what element is in the second row, first column? So second row, here's row 1, here's row 2, second row, first column, so that would be the number 3. That's the entry or the element in this spot. So just being able to kind of read a matrix and understand what's happening is useful. So, so normally I would talk about taking these systems of equations and making them into matrices, but we'll worry about that in another lesson. I'm just kind of going in the order of what Study Island has for you guys right now. So I'm going to skip ahead in my notes that I wrote for you guys. Let's see. So let's talk about some matrix operations. So just like with real numbers, we can operate with real numbers. We can operate with matrices as well. So in order to talk about that, I'm going to back it up a little bit and talk about equality of matrices. So again, matrices, plural of matrix. So the equality of matrices. And this may seem pretty silly and duh, like very common sense, but we say that two matrices are equal provided they have the exact same dimensions. So the dimensions have to be the exact same. And of course, if they're equal matrices, then all of the corresponding entries must be equal. So I just want to show you what I mean. So here we have a 2 by 2 matrix. It's equal to another 2 by 2 matrix where every entry is exactly the same and in the exact same spot. So these are both equal. Here's an example, or I guess a non-example. I'm still going to create a 2 by 2 matrix, but these two matrices are not equal, right? They're not equal because while they have the same dimensions, their entries, their corresponding entries are not exactly the same. So the 4 and the 5 got swapped here in the second row, therefore it's not an equal matrix. Now here's a different type of problem, which sometimes children find confusing. Okay, this is not going to be equal. Here's another non-example. Even though there are 0 zeros here in this third column, these two matrices are not equal because in order for two matrices to be equal, they have to have the exact same dimensions and their corresponding entries must be exactly the same. So while there's no other entries here, we can view it as a 0, 0. This is a 2 by 2, whereas this matrix is a 2 by 3. So because their dimensions are not exactly the same, then that's why we're saying that these matrices are not congruent or are not equal to each other. All right, so that's going to be important, being able to distinguish the dimension side of this, whether two matrices have the exact same dimensions, which brings us into matrix addition and subtraction. So I'm going to show you guys some examples. And, sorry. So matrix addition and subtraction. So just like with real numbers, when we talk about subtraction, we can just say it's adding the opposite. So adding the opposite sign. So we can think about that too with matrices. So I'm going to show you what I mean. So in order to add or subtract two matrices, their dimensions must be identical. So here I have a 2 by 2 matrix, and here I have a 2 by 2 matrix. Because these matrices have the exact same dimensions, I am allowed to add them. And adding them is very easy. All you do is combine the corresponding entries. So if this entry is in the first column, or first row, first column, I'm going to add it to the entry in the first row, first column of the second matrix. So what's 2 plus 6? And then I put the answer in the same corresponding location. So I add these two together, and I put it in that spot in the new matrix. So if this is a 2 by 2 matrix, and I'm adding another 2 by 2 matrix, let me turn that light off. Then the answer should also be a 2 by 2 matrix. So we're taking two matrices with identical dimensions, our answer should also be an identical dimension if we're adding them. So now in this spot, so row 1, column 2, I add it to row 1, column 2, 3 plus 1, I put it in row 1, column 2. I'm going to continue that. So here is my answer. I'm adding two matrices. Their dimensions must be identical. The answer, the new matrix as an answer, is going to be an identical dimension. So let's talk about if we were to subtract. And I'm going to change some dimensions here. So we have this time, what are the dimensions of this matrix? So remember, it's rows by column. So how many rows? 3 by 2. So I'm going to subtract now. So I'm only allowed to subtract if this next matrix has the exact same dimensions. So I'm going to create one. So this is also a 3 by 2. So when I subtract, my answer should also be 3 by 2. And just like we did up here, I'm going to take the entries in corresponding spots, and then this time I'm subtracting. So it's 2 minus 6. So it's negative 4. I don't like this equal sign. Okay? 3 minus 1. 2. And then I'm going to go down to the second row, move to the first column, and subtract. Negative 1 minus nada is negative 1. 4 minus negative 4. Be careful. 4 minus negative 4 is 8. 9 minus 3, 6. 10 minus 2 is 8. So here's our answer. Pretty easy, right? So adding and subtracting matrices, the biggest thing that you have to remember, the dimensions must be the same, and then your answer has to match those dimensions. And all we do is combine the entries in corresponding spots so that we can get our answer. And we just use whatever the operation is. So that's adding and subtracting. So there are properties of real numbers that correspond to matrices. So this matrix addition, for example. So if we have matrix A, we can say that this is matrix A, plus matrix B, right? If we add these two matrices, would the answer be any different if I did it in the opposite order? So what if this one was first? Would the answer to A plus B, this matrix here, be the same as B plus A? And the answer to that is yes. So matrix addition is commutative, meaning the order of them doesn't, I see that clear. So the order of them is not important when we add. What about subtraction? Is A minus B, so matrix A minus B, here's our answer, would that be equal to B minus A? So let's just check out the first. So now I'm just doing this in reverse order. Is 6 minus 2 the same as negative 4? So 6 minus 2 is positive 4. So these are not equal. So matrix subtraction is not commutative. So this is a commutative property whenever the order doesn't matter. Now, I will say, without proof, just because we're running out of space here, that matrix addition is commutative. It also is associative. So if you don't remember the names of your properties, let's say I had 3 different matrices to add together, so I was adding another matrix on at the end. So does it matter what order I add these in? So is the sum of A plus B, if I add that then to matrix C, is it going to be any different to if I changed it to adding B plus C? Sorry, there's a glare. I don't know. I'm going to go turn the light off. So B plus C, if I find that sum and then add it to matrix A, the answer is going to be the same. So matrix addition is commutative and associative. So those two properties hold true. Commutative and associative are true. It does not, however, work for subtraction, and we could check that out if we wanted to. All right. Now I want to go back to a word that you learned in your last unit with vectors. So we're going to talk about scalar multiplication. So scalar multiplication, if you remember what a scalar is just a real number. So if we multiply a matrix by a scalar, so a matrix, while it can be made up of real numbers, a matrix is obviously not a real number. It's a conceptual organization, right? It's an array of numbers. So can we take a matrix and multiply it by a scalar? Of course. So if we're multiplying a scalar to a matrix, all we're doing is we're saying, let's say 3 is my scalar, and I'm going to multiply it by this 2 by 2 matrix, okay? If I multiply a matrix by a real number, by a scalar, I have to scale every entry in the matrix. So the new matrix that's now been scaled by 3, I'm just distributing 3 to each of the entries. 3, 6, 9, and 12. So 3 times 1, 3 times 2, 3 times 3, 3 times 4. So all of the entries in the matrix have to be multiplied by whatever the scalar is. Now, a scalar can also be a negative number because it's just any real number. Now, it is possible to multiply a matrix by a complex number or something that's outside of the real number system, but that's way outside of the bounds of this class for now, especially since we are not together and we're learning solo. So let's just focus on what we need to know. So here's a negative scalar. It's okay. A scalar, it's a real number. -4, last time I checked, is a real number. So what do? All we're doing is distributing that -4 to all of the entries. So I just chose the exact same matrix here just to show you what's going to happen when we multiply all of them by -4. Easy, right? So it's just changing the sign. And that's it. Now, the complexity of matrix operations happens now. So this will be the final thing we talk about in this video. And what if we want to multiply a matrix by another matrix? It can get a little bit more complicated. So if you think about it, it's not, you can't just distribute. Or you could try, but that may not necessarily be correct. So before we get into matrix multiplication, I want to talk about just a couple definitions. And one of them, the first one, is going to be a row vector. So a row vector is very simply just a matrix with a single row. So with one row. So an example of that is just one row. It doesn't matter how many columns it has or how many entries are in it, it's just only allowed to have one row. So this is a 1 by 2. Okay, I could also have this 1 by 3. I could have this 1 by 5, right? So what do all of these matrices have in common? They have a single row, so we call them a row vector. Kind of weird, but important in a second. Now, there's also something called a column vector. So what do you think a column vector is going to be? So we follow our last definition. It's now just going to be a matrix with a single column. So here are some examples. So this is a 2 by 1. I can't remember what I did last time. This is a 3 by 1. This is a 5 by 1. Oh, you can't see it. My bad. Right? So these are all column vectors because they contain a single column, right? Single column. So the number of rows isn't important to this process right now when we're talking about the definition. It is, however, going to be important when we talk about multiplying two matrices. Now, this can get a little bit crazy, especially since I'm not in front of you and you can't ask me questions. So I'm going to try my best and go slow. Make sure you pause the video and make sure you check out the Study Island lesson on this because they do a pretty good job. They have some color coding. I only have 2 markers. I did not grab any more from school. So I am waiting on an Amazon shipment as we speak. So here's the deal. I'm going to go through this a little bit slowly, and I'm going to talk about a very basic case. So what if we take a row vector and we multiply it by a column vector? So I'm going to choose 1, 2, 3, and I'm going to multiply it by 4, 5, 6. So I'm going to stop for now, and I just want you to look at what the dimensions of these two matrices are. So this is a 1 by 3. This is a 3 by 1. Okay? So row vector, column vector. When I multiply these, essentially, it's called an inner product. And here's how we find it. We take the numbers in the corresponding entries and we multiply them together. So like first entry, right? We multiply those together. 4 times 1 is 4. And I'm going to do that for the second entries. 2 times 5 is 10. But what do I do with that 10? I add it to the previous product. And then I go to the third entry. 3 times 6, I'm adding 18 to the previous products. So I have 4 plus 10 plus 18. 4 was 1 times 4. Then we go to the second entries, 2 times 5, that's where we got the 10. And then 3 times 6 is 18. So the answer to this, when I multiply a row vector by this column vector, ends up being whatever the sum of 4 plus 10 plus 18 is, 32. Now, technically, this 32 is a matrix. So when we multiply two matrices, or three matrices, or whatever, our answer is going to be a new matrix. So this is a new matrix. What are the dimensions of this matrix? Well, there's one row and one column. So this is important right now because it's developing a rule. So in order to multiply any matrices, not just column and row vectors, any matrices, you're only allowed to multiply if these two numbers match each other. So whatever my first matrix is, I write out the dimensions. So this was 1 row, 3 columns, 1 by 3. My second matrix was 3 rows, 1 column. So do you see how these inner numbers are the same? If those two numbers are the same, you are allowed to perform the multiplication. And here's the cool part. Your answer will be the outside numbers. So the answer is a 1 by 1 matrix, and that's exactly what we saw when we did this. So I'm going to show you how to do this a lot. Obviously, we'll do a few more, but I just want to make sure we understand what we're talking about right here with these notes right here. So I'm going to draw up a couple different matrices now, and I want to see if you guys can tell me whether or not we're allowed to perform the multiplication. So is it allowed? So that's the first question we're going to answer. Is it allowed? And if the answer to this question is yes, what are the dimensions of the answer? So is the multiplication allowed? And then if it is allowed, what are the dimensions of the answer? If it's not allowed, we don't have to give dimensions of the answer because we can't find one. All right. So the first one, let's say we had a 2 by 3 matrix, and I wanted to multiply that by a 3 by 4 matrix. Is the multiplication allowed? So the way that we check is we look at the number of columns of the first matrix and the number of rows of the second. Those are what we call the inside numbers. Are they the same? Yes, which means we are allowed to multiply these two matrices, whatever they are. So right now I'm just talking about the dimensions. So now, once we've said yes to this question, what are the dimensions of the answer? So the answer would then be some new matrix, and he's going to be a 2 by 4. So it's a 2 by 4 matrix, and we will work these out. I'll show you why this is true, but for now I just want to make sure that we understand what we're allowed and what we're not allowed to do, because it would be kind of shameful to waste our time trying to multiply something if it wasn't allowed. All right, let's try another one. Is a 6 by 1 matrix, whatever it is if I tried to multiply it by another 6 by 1 matrix? So they have identical dimensions. Am I allowed to multiply them? And the answer to that is no. Multiplication is not allowed. Why is it not allowed? We look at this number and this number. These are the two numbers that must be the same to perform matrix multiplication. So if we were trying to add these two or subtract them, we would be perfect. We're in the exact spot that we need to be. But the multiplication, these two numbers are the ones that must match. So it can be a little bit confusing, and we understand that. So because it's not allowed, don't even worry about what the answers would be, because we can't multiply them, so there wouldn't be an answer. All right, let's try another one. What about a 2 by 3 matrix? What if I wanted to multiply it by a 3 by 3 matrix? Am I allowed to multiply these? So again, I look at this and this. So the columns of the first, the rows of the second, these are the same. So yes, we are allowed to multiply. What are the dimensions of our answer? So we look at the outside numbers. Our answer would be a 2 by 3 matrix. All right, so hopefully we understand what to do, or maybe you don't understand what to do yet, but you understand when you're allowed to perform matrix multiplication. And now we're going to talk about some examples of this. All right, so let's see what I have for you. Okay, perfect. All right, so I'm going to define a couple matrices for right now. So in general, we do this with a capital letter. So let's say matrix A is defined as 1, 2, 3, 4. Feeling very creative today. B, matrix B, is 5, 6, 7, 8. And the first operation I want to perform is A times B. Matrix A times matrix B. So thinking about, are we allowed to do it? 2 by 2, 2 by 2. So yes, we are allowed because this is a 2 by 2. This is a 2 by 2. These numbers match. Multiplication is allowed. These give me the dimensions of my answer. So that's what I want to talk about right now is the dimensions of our answer. So the product is going to be a 2 by 2 matrix. So this is just me drawing a template. I have 2 rows, I have 2 columns, okay? So the template is kind of helpful so that you know how many numbers you are trying to find. So here's the weird part. I want to go back to that vector multiplication that we talked about. So when we're multiplying A times B, we focus on the first row of matrix A and the first column of matrix B. So in order to get an answer in the first row, first column, right? First row, first column, that's this right here. I'm going to do what we previously did. I'm going to multiply this row vector by this column vector. So this spot right here, so I'm going to put a little dot because that's the one we're focusing on. It's going to be 1 times 5 plus 2 times 7. 1 times 5 plus 2 times 7. Sorry, I didn't write it. So 2 times 7, 14. So when I multiply this row by this column to get the row 1, column 1 product, it's 5 plus 14. So the first number I'm going to write right here is a 19. So now I want to go to the first row, second column, and in order to get that answer, I still work on the first row, right? I'm still in the first row. So to get this answer, first row, but now he's in the second column. So I don't want to use the first column, I move to the second column. And I'm going to do the exact same steps. 1 times 6 is 6, plus 2 times 8, 16. So what am I getting here? 22. That's what goes right here, 22. So I'm done with the first row. Now I move to the second row. So when I come back up here, sorry. Go ahead and do this too. Okay, so when I go back and I multiply A times B, Now I'm working on my second row, right? I'm on my second row. These two numbers are on the second row. This number is the second row, but it's the first column. So to get this product, I do second row, first column. 3 times 5, 15, plus 4 times 7, 28. So 15 plus 28, 43. That's what goes right here. Okay? Finally, to get this answer, I'm second row, so I'm still using second row, but I'm second column. So I don't want to use 5 and 7 again. I want to go over here back to 6 and 8. So see how I'm doing these two vectors here to get this inner product. Inner product. 3 times 6 plus 4 times 8. So together, that makes 50. This is our final answer. So it's a very systematic way of doing this. And if you take your time and don't try to rush, it's easy. You just have to take your time. And after you do them a few times, you'll be set. It's not really complicated. It's just take your time and go slowly so that you see all the working parts. Now, what I want to talk about is I'm still going to use matrix A and B up here, but now I'm just going to rewrite them for us. But now I'm going to find a different product. What if I, instead of finding A times B, what if I did B times A? Would we get the same answer? So is matrix multiplication commutative? So let's try B times A. And then we'll come back to this up here to see if we got the same answer. So B times A, I'm just going to do it on a piece of paper since we have limited space here. All right, so B, matrix B times matrix A. So again, always check to make sure that you are allowed to do the multiplication. But because these are what we call square matrices, because the dimensions are the same, right? Kind of square. So 2 by 2, 2 by 2. So I'm going to rewrite these just so we have them right in front of our face here in the right order. By that I mean it's B times A. B times A. So 1, 2, 3, 4. So if it's a 2 by 2 and a 2 by 2, we can multiply. That's good. And then here are our answers. So our answer is going to be another 2 by 2. So I like to draw the template when I'm beginning to do this because it just gives me a guideline so that I don't have too many answers or not enough answers. All right. So the first spot, row 1, column 1, I'm going to take row 1 and column 1. 5 times 1 plus 6 times 3. So 5 plus 18 is 23. If we compare that first answer to this one, we can see it is not commutative. So A times B is not equal to B times A in matrix land. Real numbers? Yes. Matrix land? No. So I want to just finish this so that we can see just another example of multiplication. So what if now I want this answer? So I'm still in column 1, so I'm still using 5 and 6, but now I want to go to column 2. I think I misspoke, but you guys see what I mean. Row 1, column 2. Row 1, column 2. So these are the vectors I'm going to use. So it's 5 times 2, or 10, plus 6 times 4, which is 24. So we can see this one is going to be 34. It's an inner product is what they're called. I keep forgetting to say that, but it's an inner product. All right, so here, and this is our second row. So I'm done with this guy, and I'm going to use my second row to get my inner product for second row, first column. I use 7, 8, 1, 3. 7 times 1, 8 times 3. 7 plus 24, 31. Second row, second column, second row, second column. So now I'm done with this guy completely. 7 times 2, 14, plus 8 times 4. All together, 46. So you can see these two matrices, while they have the same dimensions and we use the same matrices to get their product, the products are not the same. So matrix Multiplication is not commutative. All right, so I'm going to try a bigger one now for you guys, just so you can see when they're not square matrices like this, is it possible to multiply them? Yes, as long as it meets that criteria that we talked about a second ago. So now we're going to say multiply matrix A times matrix B, where matrix A and matrix B, I'm going to use this 5, 6, 7, 8 again, but I'm going to add a couple numbers here. So now what we've got, 2 by 2, but this isn't, matrix B isn't square anymore. Matrix B is 2 by 3. So are we allowed to perform the multiplication? Yes. Right? What are the dimensions of our answer? A 2 by 3 matrix. So let's go ahead and draw that. A times B is a 2 by 3. 2, 3, 1, 2, 3. So I'm just setting it up because I'm new at this, right? Setting it up so I don't make any mistakes. All right. So to get the answer in row 1, column 1, we use row 1, column 1, and we find the inner product. So we multiply corresponding entries. 1 times 5, right? So most of this matrix is going to be the same as what we just saw in the previous one. What I want to talk about is this final answer. So 1 times 2, or sorry, row 1, 1, 2, 5, 7. So 1 times 5, 2 times 7, and then I add those here. So we're still getting 19. Row 1, column 2. So 1 times 6, 2 times 8. I add those together. I'm still getting 22. Here's our new column that we didn't see on the last one. So it's still on row 1, but now I have a third column. So that's how I'm going to get this inner product. So it's 1 times 0 plus 2 times 1. So this is a 2. Now I'm ready to start finding my inner products for the second row. Second row, first column goes here. So again, 3 times 5 plus 4 times 7. And we know that was 43. Now I'm moving second row, second column, 3 times 6, 4 times 8, add those together. What do we get? We still get 50. So now I still have a second row, third column spot left. Second row, third column, 3 times 0 plus 4 times 1. Easy. So we can see this is going to always give us a 2 by 3 here whenever we multiply, or whenever we have. So in general, your product will always have the number of rows of your first matrix and the number of columns of your second matrix. That's standard always and forever. All right, so hopefully you found this helpful. Those are the operations that you are required to know right now. So we're going to talk about others and what some of the other cool stuff we can do with matrices throughout this unit. Just please make sure you keep up with your Study Island lessons, not just the questions, do the lessons because they're helpful. And let me know if you have questions. So don't forget, every Monday, 10:30, we have our Zoom. You're more than welcome to check in and ask questions then. Alrighty, see you next time.